Hello and welcome. We begin with gravity, the force that makes apples fall to the ground and keeps planets circling the sun. Gravity is simply the pull between any two objects that have mass. Isaac Newton was the first to put this idea into a precise formula back in 1687, but as we'll see, Einstein gave us a deeper picture. In this course, we'll explain gravity using space-time geometry. Newton's three laws of motion describe how objects move under forces. The first law, inertia, says an object will stay still or keep moving uniformly unless a force acts. The second law, F equals ma, relates force, mass, and acceleration. The third law says forces come in equal and opposite pairs. These laws, together with Newton's law of gravity, explain much of everyday motion. Newton described gravity as a force acting over distance. His formula is F equals g times m1 times m2 over r squared, where m1 and m2 are the masses and r is their separation. In other words, double the mass or halve the distance and you get 4 times the force. This beautifully explained planetary orbits and falling apples alike. However, Newton's gravity isn't the whole story. A famous puzzle was Mercury's orbit. Its closest point, perihelion, shifts an extra 43 arcseconds per century beyond Newton's prediction. That tiny discrepancy hinted at a deeper rule. Einstein's theory later showed that the sun's mass actually curved spacetime in a way that explains Mercury's extra shift. Einstein revolutionized gravity by dropping the idea of a mysterious force at a distance. Instead, he showed that mass and energy warp the fabric of spacetime. Picture a heavy ball on a stretched sheet. It makes a dent. Objects moving nearby follow that dented shape. In Einstein's picture, planets orbit and apples fall because they're following curves in spacetime caused by mass. Einstein's special relativity showed that space and time are linked into a four-dimensional spacetime. We can imagine spacetime as a fabric. When nothing is around, spacetime is flat, like a flat sheet. But put a mass in it, and spacetime bends or curves around that mass. A key idea in general relativity is the equivalence principle. It states that acceleration and gravity are locally the same. For example, if you're in an accelerating elevator far from Earth, you feel pushed down just like in gravity. Conversely, in free fall, you feel weightless. You can't tell you're falling. This principle tells us that gravity can be thought of as acceleration through curved spacetime. Imagine you're in a sealed elevator that's falling in space. Inside, you, a hammer, and a feather would all float together as if gravity vanished. There's no way to tell whether you're in deep space or falling under gravity just by local measurements. Einstein used this to conclude that gravity is the curvature of spacetime, not a force you can feel in freefall. Here's a common analogy. Picture a stretched rubber sheet. Place a heavy ball, like Earth, on it, and the sheet bends downward under the ball. Now roll a marble, like a satellite, near it, and the marble moves toward the heavy ball, not because of a force, but because the sheet is curved. This is exactly how Einstein's geometry works. Mass causes spacetime to curve, and other objects move along those curves. In curved spacetime, the analog of a straight line is a geodesic. It's the path an object takes if no forces act on it. For instance, on Earth, a plane flies along great circles, like lines of longitude, because they are the shortest paths. In space, a planet in freefall follows a spacetime geodesic. Gravity doesn't push the planet. Instead, the planet moves along the curve dictated by spacetime geometry. Einstein summarized gravity with his field equations, often written as g mu nu equals 8 pi t mu nu. At heart, they say spacetime geometry equals matter-energy content. In words, the distribution of mass and energy tells spacetime how to curve, and that curved spacetime tells objects how to move. You can think of Einstein's equations as a generalization of Newton's gravity. In the limit of weak gravitational fields and slow speeds, these equations simplify back to Newton's law. That's why Newton's gravity works so well for most things on Earth and in the solar system. Einstein's theory just adds corrections for extreme cases. A very interesting prediction is that even light beams are bent by gravity. Since light follows the geodesics of spacetime, it will curve around massive objects. In essence, a galaxy or cluster acts like a lens. Einstein realized that starlight passing near the sun's surface should be slightly shifted because the sun's mass curved space there. Amazing demonstrations of light bending are seen in deep space images. For example, the Einstein cross is a single quasar whose light is split into 4 images by the gravity of a foreground galaxy. Astronomers use these lenses to study very distant objects. The multiple distorted arcs you see are real evidence that gravity bends light as predicted. Einstein's theory also changes our understanding of time. A clock closer to a mass, stronger gravity, ticks slower compared to one farther away. In other words, gravity dilates time. This means that if you lived on a very massive planet, your clock would run slower than someone far away from that planet. We actually measure this effect. Atomic clocks aboard jet planes and satellites have been compared to ground clocks and show tiny shifts exactly as GR predicts. For instance, GPS satellites orbiting Earth are farther from Earth's gravity, so their clocks tick a bit faster than identical clocks on the ground. Engineers pre-adjust the satellite clocks for about 38 microseconds per day, or else navigation would soon drift off. General relativity predicts one more novel effect: gravitational waves. They are ripples in the fabric of spacetime caused by accelerating masses, like 2 orbiting black holes. Einstein predicted them back in 1916, but he thought they would be too small to ever be detected. It turns out we've built the technology to hear them. In 2015, LIGO made the first direct detection of gravitational waves. The signal came from 2 black holes merging far away. This spectacular discovery confirmed yet another GR prediction in an extreme gravity regime. Now scientists can listen to black holes and neutron stars via gravitational waves, opening a new window into the cosmos. Black holes are one of GR's most famous predictions. When enough mass is squeezed into a small region, the curvature becomes so extreme that an event horizon forms, a boundary beyond which nothing can return, even light. Stars like the Sun would have to shrink to a few kilometers across to become a black hole. General relativity provides the exact description of these objects. The event horizon is the outer surface of a black hole, the ultimate point of no return. Imagine it as an inescapable boundary. Once something passes it, a spaceship, a star, or even light, it cannot come out. This is why black holes are black. Deep inside a black hole lies the singularity, a point where the equations of general relativity predict infinite density. In reality, we expect that quantum gravity, a theory we don't fully have yet, would modify this. But as far as classical GR goes, the singularity is where the curvature of space and time becomes infinite. Let's review the evidence for GR. First, Mercury's orbit. Classical physics left an unexplained wobble of about 43 arcseconds per century beyond Newton's prediction. Einstein's GR calculation gave precisely that extreme amount, neatly solving the mystery. This match was one of the earliest triumphs of general relativity. Another classic test was light bending. During the 1919 solar eclipse, astronomers photographed stars near the sun. The starlight was shifted by the sun's gravity exactly as Einstein predicted. This famous experiment made headlines worldwide and confirmed general relativity beyond doubt. General relativity also predicts gravitational redshift, where light loses energy climbing out of a gravity well, and clocks run slower in gravity. In 1959, Pound and Rebka measured the frequency shift of gamma rays in Earth's gravity, confirming this effect. Today, GPS satellites routinely see their clocks run faster than ground clocks by exactly the GR amount. All these match theory. In 2016, LIGO announced the first direct detection of gravitational waves, ripples from merging black holes. The signal waveform matched GR's predictions perfectly.
Similarly, the famous binary pulsar discovered by Hulse and Taylor loses energy at the rate GR expects due to gravitational radiation. These are strong confirmations in the strong gravity regime. General relativity isn't just academic. It affects everyday technology. GPS satellites orbit high and fast, so both special and general relativity come into play. Their clocks tick faster by about 38 microseconds per day compared to Earth clocks. Engineers built this correction into the system, or else positioning errors would accumulate by kilometers each day. Astronomers exploit GR effects. Gravitational lenses help map dark matter and see galaxies billions of light years away. Gravitational wave observatories let us hear colliding black holes and neutron stars. Even satellite communication networks and deep space signals factor in relativistic corrections to stay accurate. GR is woven into the fabric of modern science and technology. Einstein's equations also apply on cosmic scales. They predict that the universe can expand or contract. In fact, GR underpins the Big Bang model of our expanding universe, confirmed by observations like cosmic microwave background. Einstein once added a cosmological constant to his equations to allow a static universe. Today, that term is interpreted as dark energy driving accelerated expansion. Even with its successes, general relativity has limits. It doesn't include quantum effects, so combining it with quantum mechanics remains an open challenge. We also use GR to describe dark matter and dark energy, but their true nature is unknown. And questions like what really happens at a black hole singularity or the very beginning of the universe are frontiers of research. Future experiments and observations will keep testing Einstein's ideas. Let's summarize. Einstein taught us that gravity is not a mysterious force, but the curvature of spacetime caused by mass energy. Objects move along those curves, geodesics, so they appear attracted. His theory has passed every test, from Mercury's orbit to GPS satellite clocks to gravitational waves. Today, GR remains a cornerstone of physics. It not only explains deep cosmic phenomena, but also underlies technologies like GPS. Thank you for learning about Einstein's general relativity with me. Keep exploring